Okay, so, and hopefully this will record, it's giving me some issues. But yeah, no, this is a perfect mechanism. So again, you guys got to get in the pattern of seeing this, because this early sequence is going to be how a lot of these reactions start, right? Whether it's ethylene glycol, some alcohol condensing to generate an acetal or a ketal. In this case, it's enamine formation. But we've seen it with imine formation as well. Now, why this is an instance where it's a secondary amine, right? And so if sort of resonance form of this is what we call an aminium, right? And so those are just resonance forms that just reflects why that's such a stable carbocation, if you will. It's such a stable leaving group is because of this sort of resonance form that we've drawn here. Now, the fact that this is secondary amine, so when we talk about secondary amines versus secondary, say, alcohols, it's just a little bit confusing with the sort of nomenclature, because when we're talking about primary, secondary, tertiary amines, we're actually talking about how many groups are actually on the nitrogen, almost analogous to, say, a carbon. Whereas when we refer to like a tertiary, primary, secondary alcohol, we're usually referring to the nature of the carbon adjacent to it. So it can be a little bit confusing. So I just wanted to clarify that really quickly. But this is a secondary amine because it's got 2 carbons attached to it and 1 proton. And thus, when we're here, the only way that we can sort of fix that positive charge is by either going the reverse direction or, in essence, doing the E1 type elimination to generate the alkene, right? Now, if it was a primary amine, then it wouldn't have 2 carbons here. One of those would be a hydrogen. And why does that make this different? Because then you can satisfy that carbocation simply by removing the proton. And if you don't understand what I'm saying, and this would be, say, for example, if you had a methylamine, for example, which I've been rewatching Breaking Bad, so methylamine. I don't know, it's kind of funny, but if you use methylamine here, then you can in fact deprotonate there and get back to the imine. Okay. All right. So again, I urge you guys. You guys need to know condensation chemistry. You can assume fairly confidently that there's going to be a mechanism question on the next quiz, which is next week, that's going to be related to condensation chemistry. Okay, you can almost be certain that there'll be a question on condensation chemistry of carbonyls or some related mechanism to it that's going to require you to understand carbonyl condensation type chemistry type mechanisms on the exam. You can look through all my other exams; it's common, so it's almost certainly that you're going to have something of this nature. The one other quick point that I'll make, and this is, Don, you were going to ask a question? Yes. So Don was asking whether this would actually be doing the deprotonation. So earlier I said, well, this is probably more accurate of what's going on. Dong is probably sitting there saying, wait a second, there's a whole bunch of amine around. Wouldn't that simply deprotonate it? Yeah. So again, at this step, it really doesn't matter what you use to do that elimination. It could be the carbonyl, another equivalent of carbonyl. It could be the amine. Using the sulfonate at this step is kind of a bookkeeping, and it sort of makes you recognize that the sulfuric acid is catalytic. In essence, you kind of sort of regenerating it in a way. But yeah, I wouldn't, whatever you use to promote that elimination, I think it's okay. You could use the amine, you could use the carbonyl. You're probably right that it's probably not the sulfonate that's doing it, but what's that? Yeah, I mean, you're sort of bookkeeping here, right? You're saying, you're right that there's a whole bunch more of this in there, but this is kind of nice because it becomes this sort of bookkeeping of one of this and one of this and some of this and how it goes. So I think that's fine either way, whichever you choose to do. That's certainly open for some liberalness in terms of what you choose to do. The one other point that I want to bring up is that a few people that were getting the mechanism mostly right, and I would say, yeah, I'd be okay with this as well. Now Nicole drew the mechanism through an E1-like mechanism, right, where you generate that carbocation and then that subsequently eliminated. And I think that's more likely the specific mechanism that's going on here. Some people did it more like an E2 elimination pathway. For the sake of just sort of understanding how you get from point A to point B, I think that's fine. Like, somebody actually had written E2 to suggest that, yes, it does go through an E2 reaction. I kind of told her, simply the fact that you said E2 here, I might take away points, whereas if you hadn't said E2, it would have been a little bit more left up for interpretation. So, if you want to save books space with this, I probably wouldn't care too much about a mechanism, but if you want to play it safe, and you sort of are trying to get through the exam or the quiz, and you don't want to have to draw the compound all over again, you can just sort of say, for example, E1, and then you can do something like step 1, step 2, or something like that. But again, if we're starting to nitpick at that point, I think you're in good shape. I'm not too concerned about those subtle differences. My bigger concerns are some of the issues that we saw last week. Compounds that didn't reflect the arrows that we saw. Losing track of protons, losing track of electrons when we're doing our mechanisms and those sorts of things. And so if these are the slight, small problems that we have, this is sort of more, I would say, I think we can live with this. But what we can't live with is some of those other issues that I sort of was hopefully trying to highlight last week's class. Okay? All right, any questions? Any other questions about this? You've got to know carbonyl condensation chemistry. If you don't know carbonyl condensation chemistry, it's probably reflective of some other issues that, in terms of knowledge, you got to figure out. All right, so I was asked another question that I think is a little bit more challenging. Not really that challenging, I don't think, but it's one where if you sort of understand the chemistry that's taking place, you should be able to figure out ultimately the product of this reaction. And somebody asked me to go through this one in class. In this case, I showed stereochemistry here. I had OMe. And the mechanism is lithium aluminum hydride, EHF, and the product that resulted shown with stereochemistry, although a little less concerned about the stereochemistry. You'll in essence get a couple different stereoisomers at that position, so there's a 1-to-1 ratio. All right, so let's spend 5 minutes or so. By a show of hands, how many people have actually seen this problem and have tried it already? Just so I know, yeah. So okay, so I only saw a couple hands. So let's spend. I'll give you guys 5 minutes. Try to think about this. My one piece of advice to you guys that I haven't said in class is, what is lithium aluminum hydride? Yeah, it's a reducing agent. It's equivalent to, somebody just said it's equivalent mechanistically to a hydride. What's a hydride? You know, from a mechanistic standpoint, you can think about it as a hydrogen with 2 electrons, a nucleophilic source of hydrogen. All right, we know that carbonyls can be electrophiles. I'm telling you that La lithium aluminum hydride you can treat in terms of the mechanism as H-. And with that information, if you understand the reactivity of carbonyls and you're comfortable with some of the mechanisms that we've seen, you should be able to ultimately get there. Hold on, did I do that right? Yeah. Yeah. Everybody see this? See, a lot of you guys sitting in the back. I mean, there's lots of space up front here. I guess the fans are in the back. And so this star basically means that you get a mixture of the 2 stereoisomers. All right, anybody, by show of hands, not to be embarrassed, because I won't remember that you put your hand up anyway. Is anybody struggling of where even to start with this? Okay. Hydride's nucleophile. Carbonyl is your electrophile. How do nucleophiles add to carbonyls? Start there. See where that leads you. Yep.
Do you want us to
I can go back and forth. I think for your sake, use H- is fine. Yeah, sometimes when I draw La, LAH, I'll just show the electrons between the aluminum and the hydrogen bond. And you can do that if you want, but just drawing H, I think this is, just recognize that lithium aluminum hydride is a nucleophilic source of hydride. Treat it as such way as if it was, no different than a methyl grignard or something like that, and then. Did anybody come here from Long Island today? you're struggling with the mechanism of this, what does that do? What's that? It adds an H to the carbonyl. Is that all it does? So the hydrogen adds in once, and what happens at this stage? What's more reactive? This or this? Aldehyde. So is it going to stop here? Nope. And after workup, you get to the alcohol. Okay? So you got a whole bunch of LDH in there. Use the hydride liberally here. But you got to know this mechanism to figure out this mechanism. If you're comfortable with this mechanism, just apply the information from here to this. Yes, you're correct. So, byproduct of this reaction, after all the workup is all said and done, is methanol. All right, my today's speaker is running very late. So if you struggle at this point and you don't quite see what's going on, when you see the mechanism, hopefully it will be fairly clear. Again, anytime you see a mechanism, this is one of the things I always tell people. When you see an organic mechanism, and it's the first time that you're seeing a specific reaction, it is not uncommon, even among synthetic organic chemists, to not know that mechanism. But the moment that you see the mechanism, if you couldn't draw that mechanism tomorrow, that's a big problem. So regardless of whether you struggled on this mechanism or not, ask the question, where was I missing something, and let me make sure that I get it on the next time around.
I actually wanted to show it to you.
Okay. Okay, can you tell people why you're doing what you're doing? Talk a little louder. It needs
The
to project.
hydride is attacking this carbon because
All right.
it's partially positive.
Yeah, so the hydride's the nucleophile. It's attacking the carbonyl because it's partial positive and because that's how carbonyls react with things. Whether it's under acidic conditions or whether it's under more strong nucleophiles. In this case, the hydride is a stronger nucleophile.
So we get that hydrogen here and oxygen here charge.
Right?
And then this.
Yep, you're just missing one thing there. In your product, you just left something out.
Oh, right.
So again, so that's actually not uncommon, and that's probably because he was focused on
Yeah.
the next step. He was focused on the parts of the molecule that were going to do the next part, but you just gotta, you probably would have caught it on the next thing, but it's just to keep an eye out for.
This oxygen is not
Yeah. So what happens? Same thing again. So if you just stand up before you, just stand back before you do the next part. So see what happened here is, again, if you know this mechanism, which you guys should be able to tell us, it's the reduction of a carbonyl with lithium aluminum hydride. This is going to break down, right, to the aldehyde, okay? Because this is not stable. So again, one of the points about this is even if you, for whatever reason, haven't seen the LAH reaction yet, what you guys do know, right, is a hydrate stable? No, right? Hydrate, two OHs coming off a carbon? That's not stable, right? It goes back to the carbonyl. What does that tell you about sort of carbons that are bonded to two oxygens? That if they're not stuck there because, say, for example, two methyl groups as a ketal or an acetal is, if it can, it's going to rapidly break down to the carbonyl. And that's exactly what happened here. But in this case, it just happened twice. Now, stereochemistry here, as is shown, this was coming up. Let's go back to stereochemistry later because that's another part. So let's just focus on how we got to the product. I'm going to give you space over here. Okay.
methoxide is leaving.
Yep, so the methoxide's gone, which, yep, go ahead.
Here we can just add another covalent of
Right. So lithium aluminum hydride technically has 4 hydrides to it. Again, from a mechanism standpoint of LAH, it's probably easiest, and I'm totally cool with you guys just using H minus, so you don't have to start showing the electrons push between the aluminum and hydrogen bond. So just an extra 2 equivalents of H minus are going to attack in, and without getting, yeah. So he's, for the sake of board space, hopefully you guys can all do this. On an exam, you may just want to, well, if you have time, you might just want to break it down if you have space, but, yeah, so you'll reduce both, and then at the end of the day, what you'll have is an aldehyde, the aldehyde will have reduced to a primary alcohol, and this other alcohol is a secondary alcohol. So this is perfect. Do you want to take a stab at the stereochemistry?
I actually have no idea why it happens this way.
Okay, so let's discuss. Does anybody have a sense of why the stereochemistry is what it is? Let's follow the stereochemistry through. This comes back to another point that we were making. We probably haven't dwelled on as much, but becomes important in a problem like this. This gets down to being able to redraw the molecules in different orientations. Okay, so once I break that molecule down, as is shown here, right, I can sort of leave these molecules going in this direction. And the challenge here, and maybe the little trickery with the stereochemistry here, is as is drawn, if I kept this flat, with this carbon bond, or another way to put it is, where's the proton, right? If this proton is here, looking at this molecule, where's the proton with respect to that molecule? Is it coming towards you guys, or is it going away from you guys? So we flattened this molecule. This guy's going to the left. This guy's going down. If I flatten this molecule, what's going to be the nature of these? Come this way, right? So the proton is going to come forward. This other group is going to go back. So again, this just gets down to being able to draw molecules in different orientations. Now, you look at this and you say, well, gee, in the product, that was coming towards me. Well, what's the difference between this molecule and this molecule? Just flip it over, right? Once you flip that over, now this group's going to be coming towards you, right? And so if we redraw this, we just flip it over, then the group's going to be coming, well, whatever. You guys, hopefully I don't have space down there to show, but again, you flip it over, you'll see that group's coming towards you. So that explains the stereochemistry. Now here, I'll keep it going back. That explains the stereochemistry here. But the next question is, what about the stereochemistry? So what we said is that we've got defined stereochemistry here, but we said that we've got a mixture up there. Yeah. Yeah, exactly. Can you say that a little louder?
The trivial from the top of the plane,
Planar, yep.
is half
Either face, right? So the hydride, at this point, right, the hydride could attack from either or, right? Now, I just made this problem up. I actually have no idea what that other carbon-oxygen bond was going to be, and I said, okay, let's keep it simple, we'll get a mixture. Let me ask you guys a question, though. What if we expected this, and this gets a little bit more advanced, but just hopefully breaks down some of the ambiguity and realization of some of the ambiguity that we have. What if I instead told you that you didn't get a mixture, but you got that molecule? What's that? Well, you know, but then, okay, so let me say it another way. You got that molecule instead. This is very common in synthetic organic chemistry labs. You assume you're going to get one result, and then you get something completely different. And so your initial hypothesis of, well, it's planar, it could act from both sides. Again, I actually have no idea what the product of this reaction is going to be. But let's imagine a scenario where we did get one stereoisomer, or selective stereoisomer, where they were syn to one another. Anybody want to take a stab at it? Again, this gets a little bit more advanced, but I'm just sort of asking this because it flows into the question that sort of reflects the ambiguity of this. Alex? If you got that stereochemistry, ask my students in the back. Yeah. So the argument that was made was that what could be happening here is that this group is maybe sterically bulky, and so the hydride might not want to come from the back face, so that it would come from the face that's more sterically accessible. Yeah, maybe. If that's what we got, that could be a rational argument for it. What if we got that one? Hmm? You speak up. Carbonyl. So you're arguing a thermodynamic. Sort of thermodynamic. So you're saying that. So you're saying that if I had it that way. Oh wait, no. Yeah. Yes, yeah. Sorry. Maybe. I mean, I'm thinking of something else. Usually, when you have a group in one, this is just kind of the way that things normally go, right? If you have a group, if the nucleophile wants to come away from that group, oftentimes, it's as was said, it's a steric effect. Oftentimes, when it's the same direction, as this case would be, it's coming in the same direction of the group that you have. What might that do? It might shuttle it there. It might direct it. So what could happen maybe is there's an interaction maybe between this and the aluminal oxide or something, which then helps deliver the hydride to their side. Again, this is just more advanced stuff, but we threw it up there. We explained why we thought that it would be a mixture, but I just sort of wanted to make the point that we don't really think about stereochemistry too much. But in a problem like this, there is that ambiguity, and to be perfectly honest, I have no idea what the product would be, but what we often do in organic chemistry is that we have a hypothesis, we run the experiment, and then based upon the result that's there, we understand the chemistry better than we did previously, or we hand-wave an argument that hopefully helps explain it better, and then hopefully, as a field, we ultimately know this chemistry a little bit more. All right, we've got another half hour. Does anybody have any other problems that they'd like me to go over? Yes? So this is the exact same thing as this. So this is the analogy that I was bringing up before, that it's analogous to a hydrate. This is sort of a hemiacetal, not necessarily a hydrate. So a hydrate would be so in general, what we see, and I sort of mentioned this a while ago, right, that if you have an aldehyde or if you have a carbonyl or if you have something of this nature, and you treat it with a again, you treat it with methanol, an acid, right? The product of this reaction ultimately is going to be okay, it's that. And everybody should be able to draw this mechanism to this product. Now, the reason behind this is you sort of drive it with methanol, water is lost in the system. But if you have water in that system, there's an intermediate, or even before you lose the water as an intermediate, and again, every single one of these reactions is reversible. You have what we call so this would be considered an acetal, or this is an acetal. And acetals and ketols, acetal and ketal is just aldehyde-based or ketone-based. So this is an acetal because it would come from an aldehyde. Right? But basically the same concept here. Every single step of this reaction is ultimately reversible. But focusing on this molecule here, if you had an equilibrium of one equivalent of methanol and one equivalent, or one molecule, not that you could ever do that, but just the thought experiment, if you had one molecule of aldehyde and you had one molecule of methanol, okay? And that's going to be the intermediate. The question is, which way does this equilibrium lie? Does it lie to the left, or does it lie to the right? We've seen this a lot of hydrates as well. So does the equivalent does the reaction want to favor the left-hand side of the equation or the right-hand side of the equation? So I'm hearing the left. Show of hands for left. Not as many hands I want to see. It's the left, right? And this is reflective of the fact that carbonyls, this is just one of these things that you sort of have to appreciate, is that carbonyls are, there's a certain stability that's created by carbonyls, such that when molecules can exist as carbonyls, they will. There are examples to the contrary, and I think I made a comment about this a few weeks ago. There's like, if you put like a trichloro methyl group here, those are extremely electron withdrawing, and you stabilize it. But anyway, so when you start thinking about this reaction going this direction, you should be able to push those arrows, right? So you're just pushing the same arrows here. It's the same idea, right? And also, forget equilibrium. I mean, screw it. Well, forget equilibrium here. I mean, you've got a whole bunch of LAH in here. Even if this was reversible, what's going to happen the moment you generate that aldehyde? It's going to react with another equivalent, and you're not even going to be able to go back in the reverse direction. Am I understanding your question right? Here? This one. This one. This? This. Yes. This is neutral. But this is charged. So now this is neutral and this is charged. And you've opened a ring. It's not a neutral atom. Atom's negatively charged. And even if it didn't, if this was an OH and it was neutral, you should still break that bond. Not sure that I'm following your question. You're saying sort of, I mean, I think at the heart of what you're asking is, I think, is why would this want to take on a negative charge? But that question, if you ask that question for every single mechanism that we've ever done throughout this, you could ask that same question about every mechanism that we've ever done. That's the point of when I sort of said it earlier about the majority of reactions. You know, that's why when Nicole earlier was showing the mechanism of the enamine formation, she protonated the carbonyl first to generate a positive charge, and that positive charge, every single intermediate along the way had a positive charge to it, with the exception of the one protonation, deprotonation intermediate. Positive charge, shuffle the positive charge throughout the system. Negative charge, shuffle the negative charge throughout the system. This first reaction up into here, actually all the way down, this is simply an LAH reduction of an ester, although it's in a ring, so it's considered a lactone, but same concept in terms of as far as you guys are concerned. You're reducing an ester just all the way down. Okay. Yes? Yes? Hemiacetal and acetal. So if your concerns are about nomenclature, it's worth clarifying. But it's not the end of the world. It's good to know these terms. So get them, learn them, it'll make communicating a little bit easier. At the end of the day, we draw the molecules, and that's the best way that we see it. An acetal versus a hemiacetal, when we think about a hemi whatever, usually it's sort of like a half acetal, right? So if this is an acetal, or in this case an acetal, right? And so acetal and ketals are basically the same thing, just whether it stems from an aldehyde or a ketone. But this is an acetal, okay? This is a hydrate. The intermediate is the hemiacetal. So it's sort of the half acetal, if you will. That make sense? So for your guys, for the vast majority of situations, hemiacetals will simply be an intermediate towards either the formation of an acetal or the hydrolysis of an acetal. There are instances in the literature where acetals, there are some instances in the literature where acetals can be found as stable intermediates. In general, it's when they're part of ring systems. So those are some of the times when you see them, but for the sake of this course, I think it'll be fairly rare that hemiacetals or hemiketals will be anything other than an intermediate in one way or another. I mean, don't hold me that. You may see a mechanism where that is the product, but usually that's if it's in a ring or something like that. And you should be able to draw the mechanism to that anyways. But don't worry about why a hemiacetal will form, because for the most part, it's just a halfway point in the mechanism. I saw a hand up over here. Did I not? Did you have okay, maybe they were, yeah. Oh, THF, sorry. So THF is, anybody know what THF is? Hit right here, it's just solvent. Yeah. Yes, yeah. Yes. So the question was asked, you know, and it's one of these things. One of the things that we organic chemists will do. It's one of the things that we organic chemists will do is, you know, virtually every reaction. And I say this, but it's not entirely true. But most reactions where you're under these sort of charged conditions, right? If you have a strong nucleophile like lithium aluminum hydride or a Grignard, or conversely on the opposite side, if you're under strongly acidic conditions, once the reaction is done, with few exceptions, there's always an aqueous quench at the end. And what that aqueous quench does is, anybody know what the aqueous quench does at the end? Yeah. So from a safety standpoint, right, if you have some extra LAH in there, well, it's going to quench the excess LAH. What else might it do? Yeah, a lot of the salts and stuff. Any salts that might otherwise be in the reactions, you can just wash them away. So the aqueous workup stands to both neutralize the system by quenching the reactive intermediates, and also serves as a first purification technique to get rid of any of the more water-soluble salts and other reagents that would not otherwise be in the organic. So it'll always be assumed, kind of.
So in that final conversion of the negative charge and oxygen to the alcohol,
Yes.
it's in the
Yeah. So the question comes, well, where is this proton coming from? How do I put this in the mechanism? And yes, at the end of this step, when the reaction's all said and done and it's completed what you're going to do, there's an aqueous workup at the end, and that generally will neutralize the molecule which you've made. So does that make sense? I know it can be a little bit confusing at first. It's just, but it's just one of those things that I guess you have to. And you guys have done this in lab courses, right? Like you guys said that you ran a Grignard last year, right? Did you? Or this year? Last year? This year. This year. So you've run a Grignard early this year, or you're going to? Tomorrow. Okay. So you will see at the end of the Grignard there's an aqueous workup. So that will be an example that you'll clearly see in a practiced sense why you would do that. So, all right, I saw a hand up. Didn't you have your hand up? Didn't you just have your hand up? I swear to God, I must be losing my mind. Did I see enough? You maybe. Yeah. So. Wait. Plus the what? Oh yeah. So you will get a synthesis question, as I stated. It won't be the most difficult synthesis question, but you'll have to string together a few reactions, and from that standpoint, you're going to want to know all the reactions going all the way back. So again, it's cumulative. So for a synthesis question, you'll want to go all the way back. The focus of the exam will be on 11 and 16. Quiz will be focused on 11 and 16. I'll have to double check to see what 16 takes you through. Is 16, so is carbonyl, I mean, I try to lump these all together. Aldehydes and ketones. You really should. I mean, today, because what we just discussed today, I mean, this is within the frameworks of this. This might be a different chapter, though. Is this 16 as well? But esters, I know there's a chapter that's like carboxylic acids and derivatives or something like that, but it's all the same. I don't know why they separate those. Carbonyl chemistry is carbonyl chemistry. What's that? What's that? 17, yeah. And I think that's what this, I think this reduction is technically in there. But again, it's if you learned LAH with ketones, yeah. Anyway, yeah, hydride reduction. Yeah. So, but yeah, I mean, I'll try to keep to what I said in the syllabus, but I would strongly urge you guys to really consider, I guess, 16 and 17 one and the same, because mechanistically, they're all carbonyl chemistry, and you recognize the difference between, say, an ester and an aldehyde, because at the end of the day, I mean, maybe I'll just make one point here, because a lot of it's the same, yeah.
Sorry.
Okay.
Will you take reagents from 16 and 11 and apply them to carboxylic acids, or will you expect us to know reagents that are unique to 17? Because it's hard, because otherwise I will read all the
Yeah.
but otherwise
I think that the point of the quiz, all right, so here's the deal with quizzes. The point of the quiz is to make sure that you're keeping up with material. If I said 11 and 16, the focus will be on 11 and 16. I would strongly urge you guys, though, to be considering 17 as part of 16. I will make sure that you will technically not need to have read chapter 17, but I may also make it easier for people who have read chapter 17 if you catch my drift. So carbonyl chemistry is ester and carboxylic acid derivative chemistry. It is the same thing. So I think when I wrote that, what I was trying to do for the upcoming exam, which will be coming up in a couple weeks, was I wanted to be through all the chemistry that involved carbonyls, because carbonyls is a lot. I recognize that. But they should all be sort of lumped as closely together from a mechanistic standpoint together as possible. And so it's in your best interest to sort of keep those two chapters collectively together in your mind. But let me just make a really quick point about what we just said there, because, what are the differences between, let me make a bigger point here. So here's a point. Yeah.
Just a quick question while we're on that topic. So, for example, if we are to do chapter 17, should we learn like acidification also? All those reactions.
Those two reactions are the freaking same thing, mechanistically. If you truly understand the mechanism to this, whether or not you've even seen the mechanism of this, I expect you to be able to know it. So, answering my question before, if you know this, there is no reason that you shouldn't be able to know this. And that's my bigger point of the question that was asked before. I would think that a mechanism like this, because you know this, even though this might not have popped up till chapter 17, it is my belief that if you know the mechanism for this, if you truly know the mechanism for this, then this should be easy. Or at the very least, you should be able to come up with something that's good enough. Okay? So, if you've never seen this reaction before, try to figure out the mechanism of it before looking it up. And if you can't do that mechanism, then ask yourself, do I know the mechanism of this? Okay? All right. So, focus, know this. And it's the same thing with, say, for example, and if you know that, Walter White methylamine. Amine. Right? Now that's a little bit different. So there is a reaction. Let's skip ahead to another esterification reaction, because this is the bulk of the esterification. I don't think you guys are learning like DCC coupling chemistry for ester formation or for amide formation and the mechanisms of these things. I don't recall. I think they learn it in peptide synthesis or something like that, but we don't spend too much time in depth of it. But the one other ester, but again, I hope that you guys, one of the real big points that I'm hoping to drill home here is that for the vast majority of reactions that you see, even if they're new, they shouldn't really represent anything new to you. It's just an extension of something that you've seen in the past. So here's something, again. If you can't get the mechanism for this, I'm going to guess you don't know the mechanism of this. Okay? But here's something slightly different that I might not necessarily expect. But in the last 10 minutes, I'll put this up here. I want to spend 5 minutes, have you guys try this if you've seen it in the past and you already know the mechanism. That's fine. But here's another type of esterification that might look very, very challenging and tricky, but I'm betting that if you guys thought about it enough, you could probably come up with the answer to this. And the product of this reaction, now again, if I didn't ask, so this I would feel totally comfortable asking, even if I hadn't said to focus on 17. This one comes up in 17, it's a little more challenging, so this would probably be unfair for the quiz. But it's diazomethane esterification of a carboxylic acid. Okay, so what I'm going to do is I want you guys to spend like 3 or 4 minutes, and it's actually a fairly quick mechanism. But my hint to you guys is, think about the resonance form of diazomethane. What is that diazomethane's resonance form, and might that help you? Is here? This is really good. Okay, so I've seen quite a few people get this, which is after Monday, when a reaction that we had looked at and that you should have been studying and that you should have known, struggling with. This is good. I mean, I'm seeing a lot of people, I think, getting the general nature of this mechanism. Does anybody want to put it up on the board? We really don't have much time. So let me just sort of go through this really quickly. So I mentioned that, the hint was that I thought might be easier to see what was going on was to draw the resonance form of this. The resonance form of this, again, you got to be careful, and if you struggle to draw the resonance form of this, which I'm betting that some of you did, you really got to pay attention to the electrons, right? Some of you might like to basically draw the resonance form. It's a little challenging, right? Because you got to push electrons there, but then you got to, again, this is a situation where you kind of have to draw a second arrow, right? Because you've broken the octet rule on that nitrogen. So you got to push the other electrons up there. So this nitrogen, this is an interesting one because the nitrogen never becomes neutral, right? The nitrogen is in the middle. So always got to have those 4 bonds too. Well, you can maybe push electrons directly onto it, in which case this becomes a nitrine, but then you don't have a full octet here, so it's not quite as good. But the resonance form of this is that molecule there. And once you draw this resonance form, the reason why I sort of gave this as a hint to draw it this way is that that resonance form, I think, really reflects and might stick out to you the broader nature of the mechanism. What do we have on this side, and what do we have on that side? You see that you have the ability to have nitrogen as a leaving group, right? The nitrogen has a positive charge on it, so this nitrogen has the ability to be a leaving group. You also have an anionic carbon, which when you see in the product there's 3 hydrogens, and you look up here and you see a CH2 that has an anionic charge to it, which then ultimately has the potential to pick up an additional proton. Oh, and by the way, the starting material happens to be a carboxylic acid, right? Then hopefully you can put those things together and come up with the mechanism. And so some of the mechanisms that I saw had this attack the carbon first and lose nitrogen first, which is, if you don't know the mechanism, that's okay. But really, you've got an acidic carbonyl here. You've got that guy there. And so the first step of this reaction is deprotonation. That's simply acid-base chemistry. Okay? And then, that's something you should have, the next step in this reaction is something you guys should have been able to do, last April, right? Because what is that? The next step is straightforward to all you guys. Right? It's just a substitution reaction. The nitrogen is really good. So does everybody see that? So again, new reaction, maybe you haven't seen it before, but it shouldn't be anything that seems foreign to you. It simply builds upon stuff that you've had. So again, and I'm telling you guys, this one, if I'm saying that this one, which I just hopefully convinced you guys you should probably be able to figure out on your own, is something that might not be fair game, but this one is fair game, then a lot of the things, I think that the whole new lesson is that chapter 11, or chapter 17, you should probably look through and try to find the instances where it's basically chapter 16 being applied to slightly different, a different type of carbonyl. So, okay? All right, so good luck on the quiz next week. And then the exam's going to be coming up fairly quickly after that. So use this as a gauge for how you're doing. Oh, final comment. We have a speaker I mentioned on Monday. There is a speaker today, guy that I've gotten to know pretty well from some Gordon conferences that we've gone to. He's from Stony Brook. He's a synthetic organic chemistry. He works on a lot of fluorocarbon chemistry. There's things posted out there. It's in 1141 New Ingersoll at a little after 2 o'clock. So again, if you have the time to be there, I would go there. Because of that, I am hosting him today, which means that my office hours, I'm probably going to cut them extremely short. So right now I'm going to go make sure that he's gotten to the right places, then I'll go to my office and I'll be free for maybe a half hour. So if you got to talk to me, come to me fairly soon. So, yeah. Stop this.